Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. And today we'll be talking about operation of Distribution Phasor Measurement Unit, popularly known as D-PMU. Now, when you concentrate on the topic Phasor Measurement Unit, it is quite popularly being used and explored its capability in transmission system. However, even in distribution system, phasor measurement unit can play a very important and critical role which can replace most of the analytical information that we receive through ADMS. Perhaps actually it can enhance the capability of distribution system analysis to a larger extent. Now, traditional phasor measurement units, PMUs, have been widely adopted in transmission system for monitoring and control, and they are emerging as essential components in active distribution system too, particularly due to the increasing integration of renewable energy resources and active consumer participation. However, there are a bit of challenges. High cost historically hindered PMU development in distribution network, but low cost distribution PMUs, phasor measurement units, example micro PMUs, now make deployment feasible across the distribution. Now, enhanced resolution, phase angle accuracy and affordability make distribution PMUs or micro PMUs suitable for complex distribution systems. Now, if you see the basic structure of a PMU, as you could see, this is my power system, then we have instrument transformer, then we have filters, then GPS satellite signal through GPS receiver, and then precision internal clock, A to D conversion, then moving to phasor processor, and then communication model to a communication system. So, this is overall the architecture or the structure of an PMU which is currently in place for our distribution PMUs or micro PMUs. Now, if you see the schematic of PMU installed in power system, now we do have actually control centers, we have power plant substations, transmission substation, distribution substation as well as in microgrid. And you can see the PMUs can be placed in the substation transformer, in the transmission corridors, and we can have actually in renewable energy resources, wind energy resources, residential buildings, as well as in distribution substations, as well as in transmission substations. There are n number of scope for the micro PMU to be placed, starting from the generation side to transmission side to distribution side, including the microgrid having many renewable energy sources connected to my control center. Now, summary of distribution PMU based applications, there are many, but to specific few: system state awareness, under which we can do frequency monitoring, topology verification, state estimation, harmonic state estimation, DR output and reverse power flow monitoring specific to renewable energy, voltage stability monitoring, dynamic feeder rating. So, these are all system state related issues can easily be monitored using distribution PMU, that is phasor measurement units. We can also use D-PMUs for event detection, that is event detection and classification, voltage fluctuation detection, low frequency oscillation detection, unintentional islanding detection, fault detection and fault localization, high impedance fault detection, fault induced delayed voltage recovery detection is also possible using D-PMU. So, the D-PMU has many applications. Even if you look into the operation auxiliary side, intentional islanding can be detected, distribution system restoration is possible, economy dispatch is possible, phase identification, and finally, the data mining, that is post-mortem analysis, model calibration and validation. All those dozens of applications easily be enhanced as possible using D-PMU. Now, what is synchrophasor technology? That's a very, very important. What is synchrophasor technology? Now, core functionality, that is a distribution level phasor measurement unit, measures phasors, amplitude and phase angles of sinusoidal voltages and currents. Also provide frequency, rate of change of frequency, that is ROCOF, and optionally harmonic phasors and sequence components. Now, when you talk about data acquisition model, where samples voltage and current waveforms, typically 2880 hertz for 60 hertz and sometimes reduced to 50 hertz, uses instrument transformers, anti-aliasing filters and analog to digital converters. Now, then we have a synchronization model in which we synchronizes data using pulse per second PPS signals aligned with coordinated universal time UTC, accuracy which is less than or equal to 1 microsecond. And there are two major methods: discipline acquisition, PPS controlled local clock directly; free running acquisition estimates offset between local clock and PPS, less accurate but flexible. Now, then move to computation model in which we extract phasors using algorithms like discrete Fourier transform, DFT, which are most common, and then direct model matching and wavelet transforms. Accuracy depends on window type, that is Han or rectangular, and window length, which is 2 or 4 cycles. Frequency and ROCOF are computed either from phasor post processing or via dedicated algorithms. Output typically generated at 25 to 120 hertz rate. And then communication model, which transmit result to phasor data concentrators, PDCs, using media like copper or fiber via TCP/IP protocols. Data packets include measurement values, synchronization quality, errors and protocol specific metadata. Now, distribution PMU based system state awareness application focuses on monitoring system operation situations in real time and providing system status continuously and periodically, and which has many applications like frequency deviation, topology verification, state estimation, harmonic state estimation, DR output and reverse power flow monitoring, voltage stability monitoring, and finally dynamic feeder rating. Now, focusing on frequency monitoring, so frequency deviation is a key indicator of generation load balances, that is leading to system stability and equipment safety. Now, distribution PMU can directly measure both frequency and rate of change of frequency, so called ROCOF. Compared to traditional devices, networked D-PMUs offer synchronized, multi-point and high accuracy frequency monitoring. Distribution level waveforms are more prone to noise and harmonics, necessitating advanced frequency estimation algorithms in the distribution PMUs. While single phase signals can be used, three phase measurements are preferred for more robust and accurate estimation in unbalanced systems. Displayed frequency is typically the average across phases or the frequency of the positive sequence components. We can see the frequency deviation monitor, how the frequency signals vary with respect to time. Now, moving to topology verification, distribution network topology is crucial for system monitoring and control, but often becomes outdated after reconfiguration, and hence periodic identification is essential before application like state estimation or reconfiguration. Traditional methods minimize state estimation residuals, which can be enhanced by incorporating D-PMU synchrophasor data for improved accuracy and performance. Pattern recognition and data-driven approaches using D-PMU measurement, example, voting-based detection, trend vector matching, and full grid reconstruction without prior topology are emerging, showcasing a shift towards machine learning and big data-driven solutions. Now, in case of state estimation, distribution system state estimation, which is a very important aspect in distribution system that estimates system state variables, example voltages using redundant measurement and network information. Compared to transmission system, DSSC is more challenging due to heterogeneous devices and unbalanced configurations. Benefits of D-PMUs over SCADA for DSSC, because SCADA for some extent can do most of the applications that we have mentioned in case of D-PMUs, but D-PMU have an extra edge over SCADA system. Now, D-PMUs offer higher measurement accuracy compared to SCADA system. Synchronized magnitude and phase angle data is possible. Higher estimation resolution is certainly achievable. So, these advantages makes D-PMU valuable for improving DSSC performance and enabling linear models. So, now the value of distribution system state estimation, as you could see, measurement and network data, state estimation, loss monitoring, load and RES profile creation, detection of voltage limit violation, detection of asymmetry, fault localization and outage handling. So, these are different applications we can carry out using D-PMU's application to state estimation. Now, if you take a case study here, if you see the figure 54.4, this is a system which talks about purely radial network, as you could see, and figure 54.4 shows the system diagram and measurement setup for buses 15, 49, 63 and 75 as a case study with SCADA as well as D-PMU configuration. So, we like to see which is performing better compared to the other one. Now, the three test cases were run 500 times each. The case A where actually we SCADA voltage magnitude with 3% error, case B SCADA voltage magnitude with 1% error, and case C D-PMU voltage magnitude 1% and phase angle of 0.01 radians. Now, what it has been observed with all the three cases, now the case C significantly outperforms case A, confirming that higher accuracy improves DSSC results. Now, the case C outperforms case B for 70% of the phases, 170 out of 244, and has a lower average RRMSE, that is 0.1483% versus 0.1551%, highlighting the added value of phase angle measurement means the D-PMU is certainly doing a better job compared to SCADA system. Harmonic state estimation, which is an important aspect in distribution system, where power electronic devices, especially converters for renewable DRs, introduce harmonic pollution affecting power quality, equipment lifespan and line heating. D-PMUs can estimate synchronized harmonic phases, aiding in system monitoring and protection. Harmonic state estimation, which is HSC, locates harmonic resources and estimates harmonic voltage current distribution using harmonic synchrophasors from D-PMU, and that model includes WLS based HSC extended from fundamental frequency DSSC, HSC with power bound and weight adjustment for improved accuracy. Singular value decomposition SVD is used when full system observability is lacking. Now, DR output and reverse power flow monitoring is an important aspect, as I told you, especially for renewable energies. If all the energy available at lower point of a distribution feeder If a huge amount of actually renewable penetration do exist, probably all the energy cannot be consumed by the local load, and hence it has to reverse back to the high voltage distribution systems. Now, monitoring those reverse flow is an important aspect. So, D-PMUs and DR interconnection points provide high resolution measurements for real-time monitoring of DR output and reverse power flow. These measurements support performance evaluation and accurate revenue settlement for DRs and prosumer systems. Now, front of meter, that is DR, can be monitored directly with distribution phasor measurement units. Behind the meter DRs are harder to measure due to limited visibility. Data-driven methods using historical data and machine learning are being developed to estimate behind the meter generation. Traditional distribution systems are designed for unidirectional flow, but increasing DR integration leads to bidirectional flows. Reverse power flow can cause voltage rise, affecting feeder stability. Phase angle data from D-PMUs is key for determining power flow directions, adding protection and voltage regulation. Now, voltage stability is vital for the secure operation of distribution systems, especially with high DR penetration. Real-time accurate voltage stability assessment, that is VSA, is essential to prevent voltage collapse. Now, categories of voltage stability assessment methods. Let us start with actually single location based method. Use the single port approach with Thevenin's equivalent modeling. Easy to implement but low accuracy due to unrealistic assumptions. Example, system remain unchanged during load variation. Moving to next category, that is wide area based methods. Use non-synchronized or synchronized measurements. More accurate as they capture system changes and dynamic behavior. Example, coupled single port method, linear index method. Now, as you could see, power system integrated with DRs, we have generation, transmission, and then you have a distribution system, then you have EVs connected, wind connected, solar connected, battery connected, and then you have smart residential loads connected. Now, moving to event detection and classification, where event detection identifies anomalies or disturbances in the distribution system, often followed by event classification for future analysis. Events of interest typically affect system stability, operational security, or power quality. Hierarchical detection uses both local and wide area D-PMU measurements with steady state violation as indicators events. Centralized methods account for D-PMU measurement errors and data losses, with phasor data concentrators PDCs used for data recovery. Some methods specially targets events that after the system admittance matrix, whereas in case of machine learning methods, example semi-supervisor learning, where enables detection with labeled, partially labeled or unlabeled D-PMU data. So, fault detection classification system FDC, as you could see that the process equipments are placed, and you could see server modules, and you can say database, and algorithms are used using indicated data. Now, what is the advantage of using D-PMUs? Improve accuracy and reduce false detections for fault events already detectable by conventional means. Enable detection of short duration events, example voltage fluctuation lasting a few cycles that traditional devices may miss. Can replace or integrate functions of existing devices, example over or under frequency detection. Now, D-PMU support real-time communication, allowing for live event tracking instead of delayed post-event analysis. Now, voltage sag and swell, for example, voltage fluctuation detection is also an important aspect where voltage sag and swell caused increasingly by fluctuations in renewable energy sources like solar and wind are critical power quality issues in distribution networks where voltages are highly sensitive to active power changes. D-PMUs provide high frequency voltage sampling and fine resolution phasor reporting, enabling accurate detection of transient voltage fluctuations which traditional SCADA systems may miss. Detection methods include real-time RMS calculations using sliding windows either embedded with the D-PMUs or applied externally, though voltage fluctuations can impact phasor estimation accuracy. While low frequency oscillation are typically a concern in transmission system, they can propagate into distribution network through substations because low frequency oscillation, which is very common in high voltage network, but still they can propagate or penetrate into low voltage networks. So, distribution PMUs deployed at the distribution level, example at 120 volt end user points, have been successfully used to detect and monitor these oscillations, as demonstrated in studies from the Western Interconnection as well as in Texas. Now, D-PMUs in distribution system can both enhance detection coverage and help damp oscillations using local resources to mitigate potential impact. Now, unintentional islanding detection caused by faults or operational errors leads to unstable frequencies or blackouts. Detection methods are classified as local, passive or active and remote, example SCADA or PLCC, with local methods being cheaper but less reliable. Now, D-PMU based detection is a remote method that uses synchronized phasor data to compare frequency and voltage between the main grid and suspected islands. Now, differences beyond threshold indicating islanding. Now, D-PMU offers smaller non-detection zones than local methods and outperform SCADA without needing additional transmitters like PLCC, additional indicators, example ROCOF, harmonics, angle differences can be combined using PCA and neural networks for robust detection. Now, moving to a new area which is fault-induced delayed voltage recovery detection, that is FIDVR. So, what is FIDVR? FIDVR is a phenomena where voltage remain abnormally low several seconds after a fault is cleared. So, even the fault is cleared, still you experience a extreme low voltage, commonly caused by AC motor stalling, example air conditioners during the fault. Events often include alternating over voltage and under voltage due to capacitor bank switching during load shedding and reconnection. Role of D-PMUs in FIDVR detection. D-PMUs can track and record FIDVR event in real time, enabling early detection and effective mitigation. They offer the high resolution and speed needed for accurate FIDVR monitoring, which SCADA systems cannot provide. And we conclude this talk here. Thank you very much for your attention. But one important aspect we have learned today, that how distribution phasor measurement units, D-PMUs, so-called micro PMUs, can play a critical role for understanding the system monitoring aspect of a low voltage network, popularly renewable integrated distribution system. Thank you.